My name is Paul Busada, and I'm the director of Sequence, a company focused on engineering simulation. So I'll try and today we're going to be talking through computer modeling. So some of the motivation behind doing computer modeling, the concepts of verification and validation, what can go wrong, and that classic answer, how do I know the answer is right, if there is such a thing as a right answer. And then at the end, we'll have time for questions and discussions, and I'll do my best to share some of my expertise and experience with everybody. So first of all, I guess just a bit of background about myself. So I'm an advanced registered analyst with NAFEMS. So NAFEMS is an international association for finite element methods and standards, but it applies to some of the concepts that they promote. I think apply and are relevant to all computer modeling that's being done. So there are a list of some of my certifications in engineering simulation. I'm also a CPeng, and my practice area description is relevant to computer-based simulation and assessment of various industrial process equipment. So, a lot of the examples that I will speak to today are in that area, but I'll try and keep it as broad as possible so that everybody has something to take away from this presentation. So in terms of engineering analysis applications, so this just gives you an idea of the sort of things where I have applied engineering simulation, so everything through to fluid-induced vibration, HVAC, thermal comfort, to external aero, and even a launch vehicle, looking at hypersonic simulation around a launch vehicle. So, I've done quite a broad range of things, and over the years, you sort of start to see some common issues. And I guess I've also been involved in reviewing a lot of analysis work, both locally and internationally. And, there are some common themes that come up, common errors that people make, that we all make. And so just, really the motivation here is to try and share some of those and talk through some of the disciplines that I've sort of developed over the years to try and capture those mistakes and try and identify them when they do happen. So again, areas of expertise, mainly computational fluid dynamics and finite element analysis. But again, the concepts I think are applicable more widely than that. So why do we do computer modeling? I mean, this is a very classic quote, models are wrong, but some are useful. And I think it's really important to remember that when we're doing computer modeling, we are approximating the real world, and errors and approximations are always a part of any computer model that's being developed. But those models are useful. So, they allow us to predict the behavior of complex systems. That's obviously the fundamental motivation. And I find that as you develop a computer model, one of the most important things that you can take away from that process is that you start to understand the system. Even through the very process of developing a model, it allows you to understand what are the mechanisms, what parts of that system are important. And that's really important because it allows you to understand what's happening in your system, which leads to the next step. Without understanding something, it's very, very difficult to improve it. So computer modeling allows us to optimize or improve our systems, to check sensitivity of the performance of the system to whatever design parameters that might form a part of that system, and ultimately gain confidence that the system is fit for purpose or performing adequately. And the final step, I think that, as engineers, we need to document. We have a duty of care to document our thinking and our processes, and computer modeling allows us to document the performance and understand the performance, of some fairly complicated bits of engineering. So, I think that's also a very useful outcome of the computer modeling. So this slide I've borrowed, I've adapted from information from NAFEMS. You'll hear me referring to NAFEMS a lot. I mean, I think they're a great body because they're a non-profit organization really promoting simulation methods and standards. So a lot of the information, the guidance they provide, I think is very, very useful. So when we're doing computer modeling, we have some reality of interest, something that is happening in the real world, and we build a conceptual model of that. And then ultimately there's some mathematics that goes behind it, basically branches off. So you have some sort of mathematical computational branch, and then you have a physical experiment or the real world where maybe there are observations from site. And the first step is about verification, and that's really to do with the software that we're using. You might have a finite element software, and the fact that the finite element software is faithfully representing the mathematics, that whole process is what we call verification. Then we might produce some results and have some simulation outcomes, but we need to compare those simulation outcomes with observations from the real world, from the field, from experiment. And that's really validation. So, validating my model or validating a model is often about comparing the results with the real world, which is the ultimate, most important thing. But you'll see, for example, later on we'll talk about verification and different verification benchmark standards, and that's about making sure that the software is capturing the physics adequately. And this is a process that sometimes you can get from start to finish all in one go and everything works fine, but sometimes you get to the end here and you're starting to compare results and you don't necessarily have a good agreement with experimental data or the observations from site. And that's really a point where you need to loop back and look at some of the assumptions that have been made. Maybe it's physics, maybe it's boundary conditions. Generally speaking, if the right assumptions have been made in terms of the geometry, the physics, and the inputs to the model, then usually you would expect to see a reasonable comparison with the experiment or observations on site. So, what can go wrong? I mean, I think when I first started doing computer modeling, it always amazed me when you had a good prediction that matched experiment. I thought that was just very, very, very interesting, very cool. I've always been a bit fascinated by analysis and the concept of being able to capture the real world in a computer model and maybe predict what would happen. But that at each stage of that process, there are things that can go wrong. So we're making assumptions about the real world, and I think it's useful to list those and to try and become more aware of what those assumptions are as you're progressing through your own modeling work. So, starting at the very, very beginning, we have geometry. We're making some assumptions about the geometry. So maybe the geometry that we're modeling, we're making assumptions about what units we're using to do our modeling work. We're making assumptions about the dimensions. Is there a corrosion allowance? Is that accounted for or not? If you're modeling something that's has been built already and you're trying to understand its behavior, is the geometry in the drawings the same as built? And that often can be quite important and overlooked. People will just assume that the drawings or the CAD geometry that you've been given to do your modeling work is accurate, but that can be a point where there can be a difference from the real world there. And then simplification. So I don't know if anyone has had the experience where you are given some geometry or you're in part of a process and there's the real geometry is very, very complicated. It's got lots of bolts, maybe it's got a nameplate on it, lots of tiny little radii everywhere. And it's just not possible to include all of the geometric features in your model. So, as an analyst or engineer, you're making assumptions and simplifications to the geometry right from the start. And it's fundamental to be able to build an efficient model is about knowing which simplifications are valid or are good and which simplifications are going to cause you problems. And the classic simplification is the use of symmetry, which is a nice segue into boundary conditions. But symmetry is very, very useful, but very, very dangerous. And understanding when to use symmetry is really important. So that leads us to boundary conditions. So, you can, with one set of boundary conditions, a classic example for structures is a pinned connection or a fully fixed, a pin support or a fully fixed support. So depending on where you've set the extent of your model, the difference you get in deformations in a stress analysis, for example, between a pin support and a fully fixed support, it can make a huge difference in terms of the overall result that you get. And normally the behavior is neither fully fixed or pinned, but knowing which one to use and the sensitivity to those boundary conditions is quite important. And often, if you find you're in a situation where it makes a big difference, you're really left but no other choice but to extend the extent of your model, maybe include something like contact between the various parts that are in your model, support the model in a different way. So that's a really important thing to be aware of as you're moving forward. And then, sensitivity to other inputs that you may have. All the information that you're being provided or the inputting into your model has some degree of uncertainty associated with it. And it's really about, making conservative assumptions as you move through from left to right here. Then we might make assumptions about physics in the real world. So heat transfer is an area where we often make assumptions. We might choose to neglect radiation heat transfer or surface-to-surface radiation heat transfer in a heat transfer analysis, but that may be more important than we realize. So being able to check the physics and understand the physics and understand the approximations that we're making, I think it's really important just to be aware. Another classic example is assuming that air is constant density. That's probably fine if you're looking at flows where there's not large thermal gradients in a space, but when thermal gradients and buoyancy effects become important, that assumption could make your model meaningless. So, the default values, the default physics, or the default values will often not lead you to the right result. So it's important to try and move through your model setup in a way where you're aware of what assumptions and limitations you're making. And also, I guess, understanding, your software, all software has limitations in terms of physics. And if you're using some entry-level software, saying, what, my software will allow me to get, CAD embedded stress analysis or fluid dynamics software can be very, very useful, but has limitations. And understanding where those limitations are is really important to building valid models that make sense. And finally, I guess a discretization of that is basically how fine a computational mesh or a finite element mesh you've developed for your model. For those of you who don't know what that is, I mean, it's basically, it allows you to break up your domain or whatever it is you're simulating into elements. And the more elements or the more points you have in that model to represent whatever variable of interest you have, the better the result is, generally. But obviously, the amount of computational effort increases exponentially with increased model size. So there's definitely a motivation to use those elements effectively. And one of the big areas, common mistakes I see is, especially in fluid dynamics, is insufficient mesh refinement in the boundary layer and areas of interest. And that can have a huge impact on the results that you have. Surprising. It's just really easy to get caught out. Sometimes it makes little difference, and other times it makes a huge difference depending on what's happening in the flow or in the problem that you're trying to solve. So it's always important to be aware of that. And finally, interpretation. And this is really the hardest part for me, even after 22 years of doing engineering simulation, is interpreting my results. It requires knowledge of your software, knowledge of the codes that you're trying to maybe assess your design towards, and then knowing the different abstractions that exist for visualizing flows. For example, if you're trying to understand if there are vortex cores in a fluid flow, it can be very hard to see that by just looking at a velocity field. There are specific visualization abstractions which are used. So, the combination of all of these things means that, your model can be very, very useful. It can educate or it can mislead. And when it starts to mislead, it gives modeling a bad name. But really, it's about, if you're consistent and you try to be conservative and aware as you're working through from every stage of this modeling process, then you can avoid landing in that misleading category at the other end. So I guess, most of my simulation work has been done, has been kind of bespoke. Very little, it's not very often I get to repeat an analysis type, which is a little bit scary because, every time you're developing a new analysis procedure, there are risks associated with it. But if you are lucky enough to work in an organization which is large enough to, support maybe a quality management system, then, that really helps. But I mean, I think the takeaways are useful to all of us, even if we're working in a smaller organization. It's about having, maintaining some traceable documentation to, talking about what models have been developed, what procedures have been used, and backing up all the information associated with that, with your results. And then finally, being able to review your work with others as often as you can, so that you're not in a situation where you're out on your own and maybe there's some area we're all ignorant about something, and if you're ignorant about something, you don't know it, so it's kind of dangerous. So it's always that fear that you have in the back of your mind: have I really thought through everything? Have I looked at this from all the right angles? And even after 20 plus years of doing analysis work, I'm still calling people up, asking for advice, and trying to discuss my assumptions openly with other people. The second point, I think, is these management systems are useful because it's really important to think about the importance of your analysis. So if you're working on a pressure vessel and it's high temperature and high pressure, well, if there was a failure of that vessel, that would be a public disaster. Would there be danger to life, or is it just going to be a bit of embarrassment and an economic loss? So keeping that in the mind. I mean, we don't, no one wants to make mistakes, but mistakes happen all the time. So as you move further up that importance scale, then the importance for review increases. And NAFEMS, that little quality supplement, I think it just documents, it talks about using software that's appropriate for the analysis, having analysis procedures that, if you have a younger engineer on your team, then it's not appropriate for him to be developing analysis procedures, but maybe he can follow established analysis procedures. And really, an analysis is a product. So what we produce at the end of it is a report which has some recommendations. And so ensuring that there is quality in each stage of that is pretty fundamental. So so that leads us to, how do I know the answer is right? And I mean, I guess, how do I know? Maybe that's not the right question. Maybe, how do I know the answer is good enough or fit for engineering, for us to make an engineering judgment about whatever it is we're looking at? And this is really varies so much depending on the type of analysis that you're doing. So I'm going to talk to really the two areas where I am involved in, and the first of those is finite element analysis, and the other is computational fluid dynamics. But these checks and balances, I hope that you can find some takeaways that can be applied to your specific application area. So the first thing that it's really easy to just go, okay, I've built a model, put all my loads into my model, you get a result, it looks interesting, it looks good. So then what do you do now? So the first sort of habit I've always gotten into is just checking the loads in all directions. When I first started, I spent a lot of time using Nastran. I remember Nastran had a great little O-load output, so that by default, it would just give you a list for every load case that you'd run, what the reactions were, or the total balance of all the forces. That's really, if you're just applying concentrated forces in your model, that's not as important as if you're applying pressure loads to surfaces. It's just so easy to just select one surface that you just didn't quite need to or didn't want to, or it's what you inputting some loads and you've made a mistake somewhere. This just gives you the opportunity to capture those, to understand, and you can create like a spreadsheet. And I've got a little example here where I've just made up some numbers, and for all the various different load combinations that you're looking at, just make sure that all the loads, all the reactions in the model balance with the loads that you expect to see. That's really important. From a fluid dynamics perspective, the other no-brainer is just checking mass balances, so that all the, if you've got a lot of boundary conditions in your model and you've input a lot of data, maybe you've updated something in your model, you've changed some geometry without realizing, and all of a sudden you're putting more mass into the system than you should. So that, doing those mass balances will help you identify those sorts of errors. Energy balances are kind of similar. Have you got your heat transfer coefficients correct? Is is everything making sense from an energy balance perspective? Excuse me. So geometry checks, this is a classic, just showing a little example here on the right. Just go into your model, have someone watch over your shoulder and just check dimensions, measure dimensions on your model and make sure you know that the radii is correct. Just check a couple of dimensions here and there. It seems like something very simple, but maybe it'll help you just identify an error that was made during geometry creation, or if the geometry was sent, that the units are in a sensible set of units. Some finite element software does not have any embedded set of units, so you have to be consistent. So if you're using meters and pascals, and you've got to be consistent with everything. If you're using millimeters, you can use megapascals, but then your masses have to be in tons. And that has other implications for heat transfer coefficients that you might have in your model. So if you're lucky enough that your software, the CFD software that I use, for example, I don't really have to think about units at all, but in the FEA software I'm using, I do. So it means that you have to be very, very careful, because units is something that comes up all the time. And I just recently reviewed someone's hand calcs, and they'd done some stress analysis calcs and mixed meters and megapascals, and something was built that broke. And it's a very simple error, especially for younger engineers. But units, if they're in the right, everything is consistent, then it makes things very easy. And I for doing stress analysis, I would generally tend to prefer to use millimeters and megapascals. It just makes everything work a little bit easier. The other thing that I recommend, is doing hand calculations. So, if you can just do a few checks on the overall level of deflections, it tells you that you've got the right material properties, you've got dimensions correct. Look at some stresses away from a discontinuity, the old PR upon T for hoop stress, whatever, in your pressure vessel. That can be very useful. But a book like Rourke has got there's hundreds of different sort of hand calculations that you can do to check stresses. And I'd encourage you to get a calculator and do them with a calculator, as opposed to just more Excel. But those sorts of things are very, 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 very useful. The other thing I would look at, normally in most analysis software, you get sets of warnings or error messages. So, try and understand what those error messages or warning messages are, and understand whether there's an issue, with terms you're modeling, and if that would affect your results. So analysis benchmarks and best practice guides. So NAFEMS actually has, the first thing I did when I started my company was register the company with NAFEMS, and they send you a big box of books. That's a photo of some of them. And they make great reading in the evening when you're trying to get to sleep, but every time I read one of those books, I learn something new. And they provide some excellent benchmarks, which can be very, very useful for gaining confidence that when you're doing a newer type of analysis, that you've actually how to do it in your software. So they'll have an example problem, and you can reproduce that example problem in your software, and then compare your results to the benchmark. So that makes things a lot easier. And even though analysis software is very, very easy to use these days, it's very easy to get pretty pictures. I still think you have to be very, very, very careful. A classic example here would be heat transfer coefficients in CFD software. The software I use, if you were just to contour a heat transfer coefficient, you could look at that number and go, oh, well, that's what the heat transfer coefficient is, and run off and use that in your FEA model. But unknowingly to a lot of people, that heat transfer coefficient that's being exported is relative to a reference temperature. So it's a post-processed value. It's not calculated by the CFD software. The CFD software is calculating temperatures, and that heat transfer coefficient is just evaluated relative to a reference temperature. So the heat transfer coefficients are completely meaningless unless you know what that reference temperature is. And So really, when you're exporting a heat transfer coefficient from a CFD software, you actually can't just export heat transfer coefficients. You've got to use heat transfer coefficients. There's a way of exporting them, which it gives you a local heat transfer coefficient and a local reference temperature as a field. So you can use both of those values. You can have a relevant boundary condition that you could use in an FEA software. So this example here that I've got on the right is just showing a tube sheet here. We've got, you know, a heat transfer coefficient I've calculated. The second thing is that obviously in my FEA software, knowing now that, you know, my model's built in millimeters and megapascals, I've got to change the units of that. So they're in milliwatts per millimeter squared Kelvin. So you divide by 1,000 essentially. So you can see that in order to have a valid set of boundary conditions in my FEA software, I had to know two things. I had to know that I couldn't just export the default heat transfer coefficient. I had to use the local heat transfer coefficient with a reference temperature. And the second thing I had to know was I had to modify the units so that they were consistent across both packages. I mean, ultimately, otherwise you would have got a result that was effectively meaningless. I referred to the idea of symmetry boundary conditions. This is a classic mistake, and one I've just saw just recently with doing a review on an international project with a really high level of importance. And the people doing the analysis work overseas, which I was reviewing, had made some big assumptions about symmetry. I mean, it wasn't this isn't the geometry. Obviously, it was a fairly complex model, but the assumption, I understood the motivation to use symmetry because it effectively halves the model size and allows you to run the model a lot quicker. But you know, symmetry isn't always just about having symmetric geometry and symmetric boundary conditions. So for example, this example I've shown here is an example where I've got flow through a duct, through some baffles, and everything is symmetric, the flow is symmetric, but the response of the flow is not symmetric. So we end up with a transverse pressure wave bouncing up and down here. So, you know, if I'd applied a plane of symmetry, it would have completely removed that. The physics would have been we wouldn't have captured that phenomena at all. And, you know, that just goes to show that symmetry is just so dangerous. Symmetry in structural models can, you know, if you have buckling modes that extend beyond your sector that you've modeled and you apply some symmetry boundary conditions to that model, you just won't capture those buckling modes. Same goes for modal analysis. So symmetry has to be used with knowledge, and it kind of leads into the idea of model extent selection. So you've got to choose, knowing where to truncate your computational domain is really important. So results interpretation, FEA, this is kind of a real common one, singularity. So if you have a sharp edge and you're modeling something in a CAD embedded package with solids, then, you know, you could keep refining the mesh in a singularity and the result will just go up and up and up and up and up to infinity. In fact, you know, it's one of the difficulties associated with welds, with interpreting results around welds. It's, you know, it's a complicated area, and having the correct approach for interpreting stresses around singularities and understanding those is really important. Another comment, if you're doing a linear analysis and you have stresses above the yield of your material, obviously those stresses are not real. So the fact that the response of the material wouldn't be linear forever, there's a point where the material will start to yield and you end up with a non-linear result. So understanding the implications of that is important. It doesn't mean to say that that analysis isn't useful, but it you know, it's not 100% accurate either. So it's understanding what you're trying to get out of the analysis, and if the limitation of whatever you've modeled is affecting some of the engineering outcomes that you're looking. Equations of state I referred to, that's a fluid dynamics concept in relation to the density, how density is calculated in your flow. So assuming constant density when maybe there's buoyancy or thermal gradients in your flow, then that's not necessarily a great assumption. The same happens at high speed flows. So above Mach 0.3, then, you know, your constant density assumption starts to become less and less valid. Convergence. So convergence is, there are three areas here I'm referring to. So convergence, the first one is mesh refinement. So as you increase your mesh size, then you hope that the result converges to a answer. And that's true usually for almost all modeling, except in the area of singularities, where the answer will just keep going up and up and up. The other idea of convergence is in a nonlinear analysis that the solution converges. So that is that you have a valid solution in a stress analysis, that you end up with a situation where all the moments in your body, if it's a static analysis, is converged and it's at rest. The third reference to convergence is in fluid dynamics. So I have a little example here. In a CFD or a fluid dynamic simulation, you start off with an initial guess at the solution, and the software will iterate. This is a steady state type analysis, will iterate until it reaches some point in time where you say the result is steady, it's converged. And normally people will try and look at residuals to try and judge when a solution is converged. My experience is that it's not always useful to just look at residuals, and it's far better to actually look at whatever flow variable you're interested in. So here, these residuals have dropped, a fair amount. They look like they might have converged, but the actual variable that I'm trying to track is sort of floating around still. It may be that for the analysis you're doing, that having an answer within whatever plus or minus 2, whatever that percentage is, then that may be valid. But what it's telling me is that I probably need to run the simulation for longer, or it's telling me that the solution is not going to converge. That is, that the flow isn't steady and it might starting to become unsteady, in which case then maybe the idea of trying to capture that steady response maybe isn't valid. So having the experience to recognize some of these issues is, it's pretty important. Understanding the physics is really important. And I guess the final thing is just be super careful when trying to justify results. I think anyone who's ever done analysis at some point will have got a result that surprised them. And then you're looking at a result that surprises you. You've got two options. You either want to dig deeper to figure out why it surprised you. Is it teaching me something new about the system that I didn't anticipate? Or is there a mistake in the model? And sometimes people will be very, very quick to come up with a new theory to justify the new result, only to just realize later on there was a mistake in a boundary condition or some weird problem with the model. So, it's just very, very careful. I think, to be good at analysis and computer modeling, I think you really need to go slow and start from simple analyses, build confidence, and then from there you can move forward and to tackling more complex analyses with greater confidence. So I guess my recommendations are, just closing up the formal part of the presentation. When you go through a model, document your model. I had many, writing a formal report takes a long time. It takes a lot of effort. But it's just such a good way of documenting everything, all of your assumptions, and try and document enough in your report that someone could reproduce your work. And if you can do that, then it means all of your assumptions and all your thoughts that you had about developing that model are documented in one place. And when you come to get your inputs for your model, I still do this. You could use an Excel spreadsheet that you use to derive your inputs. You can get them from there, or you can open up the model, go and click on the field where you input the model and get it from there. And that gives you that, if you do that, then it gives you that added sort of level of confidence that you've documented what you've modeled, not what you thought you've modeled. And sometimes when you're writing a report, you can find things that you hadn't picked up on during the usual Q&A process. I've always been a big fan of creating work notes, either in a text file or an Excel spreadsheet, in a Word document, whatever works for you. Just to document your thinking, do some calculations. You can have a little justification of why you think your analysis is valid in there. And it means when you come back to a project maybe several years on, that you can look at that and understand what was done. And when you archive your projects, I think it makes common sense just to archive your projects with all your background information. I think it's important as engineers that we stick to our competence level, that there is sort of continued professional development and mentoring, that we're reading papers, and I guess you need to understand that driving software is you know, nowadays driving software is the least of your worries. You know, when I started, I started with Patreon and Asher, and it was really hard to get a mesh. You had to, you know, even to learn the software took months. These days, you know, you can get CAD embedded software, you can get a mesh and a pretty picture very, very quickly, but it's more difficult to understand the limitations, and it's more difficult to understand how to interpret the results, and it's more difficult to build valid models than it is to actually drive the software. So software isn't competence. I think it's fair to keep asking questions, doubt your results until the very end, until your confidence level increases with the result. Always I start off with the assumption that the analysis is wrong, and start to build confidence from that point onwards. And then, you know, I mean, it's just important to be transparent. You know, we're all engineers, we're humans, we make mistakes. So try to be transparent about what's been done and what checks have been made. And, you know, I think then as a result, you know, you'll gain more credibility with your analysis work, and have greater confidence in the results and in the recommendations that you're putting forward as a result of that work. All right, so that kind of concludes the formal part. I don't know whether, you know, I'm always happy to have a chat to people. Reach out to me, give me a call, email me. Happy to talk about potential projects you're working on, or if you need help or guidance, then, you know, I'm putting my hand up to help. You know, I've been doing this for 22 years, and you know, there's a lot of good work, great work being done being done right now. So, you know, I think the tools are there, and we've got to use these tools to try and make better engineering judgments.
Thanks, Paul. There's a few questions that have come in, and I would just like to say to people that, you know, this webinar is being recorded, and we will send it out to everybody that's registered. And so if you want Paul's contact details and so on, then, you know, have a look through the webinar. You'll be able to see them there, and don't hesitate to reach out. Now, the first question that we have is which software do you use, and which software do you see most used by mechanical engineers in industry for New Zealand, for FEA and for CFD?
Yeah, so I mean, I use Star CCM Plus for my CFD software. It's developed by Siemens. I've used the product since it was for about 16 years now, 16, 17 years. So since it was first developed, I think, you know, I've got a lot of confidence in it now because I've done so many projects, and I've seen it produce good results. You know, I don't think it is the software that is most used in New Zealand. I mean, I think there are lower end software that's probably more widely used. On the FEA side, I'm using Abacus at the moment. Again, you know, it's because I know it so well, and I spent a couple of summers working at Abacus HQ on the West Coast and on the East Coast and the West Coast of the States. So I know the tool very, very well, and it's, you know, really, really, really good at nonlinear analysis. I think that kind of gives me, you know, I'm pretty comfortable with those tools. I know a lot of people are using ANSYS out there, ANSYS CFX, ANSYS Fluent. I think it's really about the man and not the machine when it comes to analysis tools. You know, I think SolidWorks has a great FEA solver, which I think is actually based on the Abacus solver. So, you know, I mean, you may be driving a CAD embedded CAE tool, but actually the solver behind it is actually very, very capable. I think probably the issues really come down to making sure that you understand where the software that you're using, where it starts to run out of steam, you know, where it starts to struggle. And, you know, I think everyone knows, probably will start to feel, you know, over time where those limits are.
Thanks. And the next question is there any software in which we can build self-learning models?
Yeah, I'm not sure what you mean by that, self-learning models.
Neither am I, but so to the person that asked the question, Pankaj,
yeah, I think is that refer maybe to machine learning? Potentially, I think, you know, so, you know, I know I'll speak to this AI concept just quickly because I know that I personally have a huge interest in it and I'm watching it closely. I think it's still in the watch the space approach. So, you know, right now the state of the art with AI and CA is really, you know, you can, machine learning. So you can, if you're doing a one class of problem all the time, you could run 100 simulations or 500 simulations with build up a data set, and then you ask the machine to learn about that data set. And then once it's analyzed that data set, then you can actually almost in real time make modifications and get a result. That's very, very attractive, especially if you're doing something that you're looking for like a 1 or 2% improvement, or you're doing something that's very, very similar, that sits in the same space. The problem is, I think, for a lot of, depending on what you're doing, obviously in my area, it's not quite usable yet because everything I do is so bespoke, and you know, the software won't know if the information I'm feeding it is valid or not. You know, it's like Chat GPT. I don't know if you've ever tried to ask an engineering question. Right at the present time, it's very interesting for creating content, but the information is quite often erroneous, and because it's got so much information, it doesn't know how to tell what is valid from not valid. And the same goes for AI. So if we're throwing, if we're training a machine, then the information that goes to it has to be valid, and then from that point on, it becomes very, very interesting. So, you know, if you're designing a yacht, America's Cup yacht, and you were trying to optimize its performance, then I could see that being a really, you know, valid use. Instead, the other option right now is the other option is to actually do optimization studies, and I've done quite a bit of that and had a lot of success. You know, it's slightly different in that you're using an OR type algorithm, and the software will go away and try and optimize the performance of your design or your product. And you can get to an optimum solution in 50 or 60 design iterations. So it's still cheaper to do that than it is to do machine learning at the present time.
And the next question is, as someone who has academic background simulation, how would you recommend getting started on a professional level? Any recommended starting points?
In terms of professional level, I think you would start with simpler analyses. Obviously, if you're working, I presume that you're working as an engineer in that environment. I think it's important to start, if you're working on real problems, start with simple problems. Start with problems that you think you can get a good answer with, and compare with hand calcs. I think those sorts of things will help you build confidence. You know, I've mentioned NAFEMS, so you know, registering to become there is the option to become a registered analyst with NAFEMS, and that whole process. I don't know if there's like an entry level point where you can start and get access to some of the publications. I suspect there probably is. Also, if the organisation you work for is interested, it's not particularly expensive to join, and you get access to all of those publications. I think they give you a big box full. You can pick some initial publications, and then there are additional publications that you can purchase. But again, you know, relative to the experience that's contained in those, it's, you know, relatively minimal cost.
And can you please comment from your past experience, how and what parts of the model geometry/physics do you suggest need further sensitivity checks?
Well, you know, I think mainly sensitivity. The big thing for sensitivity for me would be where areas where you know there is uncertainty in your model, any aspect of your model where you know there's uncertainty. Maybe that's a boundary condition, probably more relevant to boundary conditions, because, you know, it's a classic situation in an FEA model. You need to constrain your body in space, you need to constrain all 6 degrees of freedom, and you've got this, you open up your CAD part. So how do I support this part, you know? And we have to make this assumptions about how to support it. If it's fully fixed, if it's pinned, that's a classic sensitivity check. Another example, you know, typical things, if in a pressure vessel, I always check is the radius, because that's just so fundamental, and the thickness. And, you know, maybe you want to check if there's a corrosion allowance, whether that's been included or not. Anywhere where you think there is some uncertainty in a data point. Material data is another area where sensitivity is often checked. You know, there are codes available that allow you to develop temperature dependent material properties, and those codes generally are conservative. So sometimes it's important to understand if you have a data set that doesn't come from a code, then maybe compare it against a more conservative data set, just to make sure that what you're doing is conservative to the best of your ability, right? So I think that's.
And the last one that we have is what analyses do you see being done relevant to the water industry? For example, CFD for optimizing geometry of pump wet wells.
Yeah, so CFD in wet wells is, I've done a lot of that over the years. And so mainly that's focused on getting good quality flow to your pumps. So I think it was a few years ago now, but I was involved in quite a large project where people had installed pumps and there was a lot of aeration and cavitation on the pumps. And when I analyzed the pumps, it was pretty obvious that there was some pretty poor flow quality entering the pump. So there is a code, the NCHI 9.8 pump intake design code, which provides some good recommendations on things on the flow quality entering the pumps. And it's quite good. They've got an experimental test where which provides specific things that you can check against. So when I'm doing CFD modeling, I'm often referencing that code and using some of the acceptance criteria in that code to say, okay, well, I've run the CFD model and the flow meets the acceptance criteria in that code. I think that's one of the most relevant areas. The other area I think is solids buildup, transportation of solids, wastewater lagoons. There is work to be done in that area. I think CFD is pretty useful because it just allows you to understand and document some of the risk, and it can be quite difficult. For example, in wet wells, for example, you can have vortex cores forming, free surface vortex cores forming, and it's not always obvious that those are going to appear, and they could be caused by the shape of dividing walls or the shape of the wet well. And sometimes some changes to the geometry of the wet well are required to improve flow into the intake and to remediate some of those vortex cores. So CFDs actually, when it's done properly, can allow you to understand and document risks associated with those issues.
Okay, and that's all of the questions that we have. I've personally learned a lot from your webinar, as I did from the first presentation that I heard. So thank you very much. I certainly appreciate that. And oh, hang on, sorry, looks like we have one more. Last one. So how long do you take to develop a simulation / project?
It can go from, I recently had a project where there was a lot of time pressure and I was able to turn something around over a weekend. That was, not a lot of sleep over a weekend. I try not to do that. Typically projects will last from, 2 to 4 weeks. I very rarely get in projects that go on for months. So most of them are, when you're in a commercial environment, you need to be able to turn around projects quickly. And, that's pretty important to me too. So, typical projects would be, 1 2 weeks to 3 4 weeks maximum.
Thanks very much. And the last part that I'd like to say, of course, is if you do want to engage Paul, then reach out early in a project. And in my experience, it's always better to engage experts earlier on and make sure that your assumptions and concepts are valid and aligned with their thinking as well right from the beginning. It saves arguments later on.